There are three. Midpoint. So the midpoint rule estimates integral from a to b of f of x dx to be approximately b minus a f a plus b over 2 plus f double prime of squiggle over 24. I keep calling it zeta, and that's actually wrong. It is a c, xic, but anyway, b minus a. And then we had our trapezoidal rule and our Simpson's rule. Trapezoidal rule. This one is degree 1, and this one is ab f of x dx. Is it no, it's actually equal because the error part makes it equal. So we can put equal signs here. Equals b minus a f of a plus f of b over 2 minus f double prime. Oh, I know I didn't do a composite midpoint rule. Okay. Over 12 b minus a cubed. And then we have Simpson's rule, which is quadratic, but I'm not going to write that down right now. So these rules that we have, when they're called the basic quadrature rules, we're just talking about doing the rules over a single interval, which is the whole interval of integration. But obviously, as our intervals get smaller and smaller, our estimate's going to be better and better. And that can just be seen by the very presence of this, b minus a cubed inside of our error. Obviously, as b minus a gets smaller, b minus a cubed will get even more significantly smaller. And as this gets less than 1, it'll drive the error down even further. So b minus a cubed implies that, and I mean intuitively it's obvious too, but smaller intervals have smaller error. So we don't want to just use a single interval. We want to use many smaller intervals. So what we're going to do is we're going to start with the composite trapezoidal rule. If we have our interval b minus a, so when I say composite, I just mean many smaller intervals. It's easiest if our subintervals are all the same length. We divide AB into n intervals and apply the trapezoidal rule on each. So we divide it into n intervals, apply the trapezoidal rule on each. So the length of each interval, or the width or whatever, is, we're going to call it h, and h is b minus a over n. So what this will look like, so say we have, a and b somewhere on our x-axis, and we have a function. And then I always, let's do n equals 4. So what we get in this case is we end up estimating using the trapezoid. So remember, secant line between these 2 points. So then our estimate is, of course, the sum of these 4 areas. The first trapezoid goes from a to a plus h, because h is b minus a over n. In this case, it's b minus a over 4. The second one goes from a plus h to a plus 2h. Next one goes from a plus h to a plus 2h to a plus 3h. And then the last one goes from a plus 3h to b. If we go back to the regular trapezoidal rule, right here, you can see that we do b or f of a plus f of b over 2. F of a will get used once, but then f of a plus h will get used twice because it's the endpoint of one interval and the starting point of the next interval. A plus 2h will be used twice because it's endpoint of one, starting point of another. So it's really just a and b that only get used once, and then everything else gets used twice. So our formula then in this case is that the integral from a to b f of x dx is approximately, and then we have, well, I'm going to write it out the kind of long, annoying way, but a plus h minus a times f of a plus f of a plus h over 2 plus, so here I've done the composite trapezoidal rule, but I've just done it on this part so far. And then I go ahead and I do it on the next interval. So actually I will have to go the next line. The next interval is, it goes from a plus 2h to a plus h times f of a plus h plus f of a plus 2h over 2 plus a plus 3h minus a plus 2h times f of a plus 2h plus f of a plus 3h over 2, and then plus b minus a plus 3h f of a plus 3h plus f of b over 2. So this is an unnecessarily complicated way to write it out, and we'll compact the formula. What we see in here, well, we first of all see that, these interval lengths, a plus h minus a is just h. A plus 2h minus a plus h is just h. So the length of each of these intervals is just h. And so what this becomes, a little more simply, is we have h times all of the f of a. Well, let's actually go one step further in simplification. My bad. We have h in front of all of these multiplying, but each of these terms is also divided by 2. So just take out the h over 2 instead of writing that over and over. So what we're left with is f of a plus f of a plus h. And then we have f of a plus h here. If I point at it with my finger, that doesn't work. If I have f of h plus a plus h here, I also have it here. So we end up with 2 of those, plus same sort of thing, 2 of f of a plus 2h plus 2 of f of a plus 3h. And then f of b is only represented once. Our integral is approximately h over 2 times, we have f of a just once, plus 2 times the sum from j equals 1 to n minus 1 of f of a plus jh, and then plus f of b separately. And if we wanted this to be an exact equality, we can add in the error term. This is the error term. Oh, this is for some Consistency, Amy. Squiggle for some squiggle in AB. Okay, there we go. That's our term. Let us apply this. So we're going to approximate the integral from 9 to 11 of ln of x dx with n equals 8, and we'll also bound the error. I'm going to go through this example thoroughly and possibly, well, definitely add in extra information about just the behavior of doing this computationally. You'll notice here that this uses n equals n equals 8. Our h is b minus a over 2. So b minus a is 11 minus 9. Sorry, over 8. I don't know why my brain is having a problem with this 8. So b minus a over n, which is b minus a over 8. B minus a is 2, the length of our interval, over 8. So h is 1/4. If we were then to apply composite trapezoidal rule, we will use this formula at the top here that I've written all over and made it worse or messy. So we end up with the integral from 9 to 11 ln of x dx is approximately, we have h over 2. So 1/4 over 2, which is 1/8. So we start with h over 2, which is 1/8, times f of a, so ln of a, plus 2 times the sum from j equals 1 to 7 ln of a plus jh, and then plus f of b, which is ln of b. In other words, this integral is approximately 1/8 ln of 9 plus j equals 1 to 7 ln of 9 plus j over 4, because h is 1/4, plus ln of 11. So then that quantity equals 1/8 times natural log of 9 plus 2 ln of 9.25 plus 2 ln of 9.5. And once you start writing something like this out, you don't even have to pay attention to what the sum says. You're just saying, okay, I'm doing 2 times ln, and then I'm adding 1/4 on each time. So instead of keeping track of the number of terms and thinking too much, we're just going to keep adding 2 ln of 10 plus 2 ln of 10.25 plus 2 ln of 10.5 plus 2 ln of 10.75. And then I know I'm done here because the next one's going to be ln of 11, which is b, so ln of 11. So if I compute this out, I get that this is equal to 4.6017. And then the actual value for our integral, the actual value for the integral is equal to the actual value goes 4.6018 and so on. So we have 3 decimal places of accuracy here. So we're essentially out of time. So it means I'll have to remember to pull up the same thing and continue this example by doing the error bound. All right, I will stop the recording.